It's going to be about using VUnit or sort of using parts of VUnit to build another open source project which you heard about already by Sebastian called this FPGA.
Sorry, can you? Okay, thank you for being here. I'm just curious, how many here are currently VUnit users? Quite many hands. How many here have never used VUnit? Welcome. Great. So why is VUnit so great? I'm not biased at all. Let's go through the anatomy quickly. At the heart, we have the very basic stuff that lets you make a test as simple as possible in the VHDL domain. We have the VHDL runner and we have the checker functions Sebastian mentioned earlier. And then you have some extra muscles, for example, data types, the array package and the queue package, stuff that you feel like it's missing in VHDL, especially if you come from system Verilog. You have the message passing interface, which was the basis for Sebastian's talk earlier. So this really will help you make a much more potent test bench for more advanced and complex systems. And then you have the little brain connecting it all together, which is the Python test runner. To me, this is largely what you experience as a Python user of VUnit when you configure tests, and also from the command line. I'm not sure that Lars will agree with this anatomy, and obviously it's not really complete. It's missing legs and stuff, but you get the gist. Sorry?
Who cares?
Who cares? Yeah. Let's limp on. So actually, I have mustered the courage to make a live demo here. The focus is going to be on this part, the test runner. And now we have used it in another project. So, a little demo, just to show you how nice it is to use VUnit from the command line. So, we use VUnit through another open source project, which is TSFPGA. So we have a single entry point for simulation here in our own development repository. And we want to run some simulations, and VUnit users will find this very similar to what you experienced with. We want to filter out tests that are in the AXI interconnect library. We can start by listing them. And we see that we have, is it 60 tests? And if we were to run them one at a time, this demo would take too long time. So instead we use 8 threads for doing that. And now the VUnit test runner is working. We gave it 8 threads on this crap top, and it can start 8 tests simultaneously. As soon as one finishes, the next one starts. And we get the test results on the fly, and soon, at the end, we're going to get a nice summary of all the tests. Yeah, and the last step of a testing framework is really getting the result to me as a user. The nice thing here is that anything fails, you get it at the bottom and you get it in red, and you will never miss it. So, who are we? Oh no, the logo's gone. Oh well. I represent TrueStream. I'm one of the co-founders. I see Frederick there, and Lucas is maybe in here somewhere. Oh, this talk is going to be about Lucas a lot. We provide design services, and I dare say we have the best customers with the coolest products. Hello Patrick, hello Herman, I saw you earlier. We also spend time and money on our internal development. This is our Potato project, which is an audio product, digital audio in. We have a 1-bit sigma delta modulator, and in the between we have FPGA for some serious digital signal processing. We provide IP cores, And these are actually the reason for this talk. We need to make AXI hypercores and other hypercores that have a really small footprint. So we were using the ones you get for free from the model. They are great in many ways. But for one, we wanted it to be simulatable with GHDL, so it needs to be readable code. And we also had to cram more into the device and manage to do that by writing them ourselves. And we spent time on open source projects, and by we I mean Lucas. And he's the maintainer of TS FPGA, which Sebastian talked about earlier. This will also be relevant for this talk. And we will start there. Oh, all of these projects use VUnit. In these cases, for its own verification, and for TS FPGA, it's part of the functionality that it delivers. So, TS FPGA is an FPGA project manager. So for us, it handles simulation and handles our builds with the model. At the base is source code management. So you follow a fixed file structure, put all your sources there, put your constraints there, and put a Python module file to define build projects and VUnit simulation. From there, TS FPGA will start simulations with VUnit and generate the ticker needed to start builds in the model. This talk is about how we steal the VUnit runner and use it for this step. We back up a bit and ask yourself a question: what to test? I have given one answer. Point number one, functionality. No matter if your implementation sucks, you really want to make sure that everything works, right? So you don't fool yourself. And number two, anything else that is important. Whatever that may be. In our case, it was the size of our IP. And we knew of no way to test that except manually, and felt that we needed to add it. To put it in other words, if a core must be small, its size should be verified. So as we have no way of doing this already, we figured that we will add it to TS-FPGA. We already have the code to run a Vidlid project. There's just a few changes that we must make. But we have a way to build one project at a time. I mean, the purpose was to build an FPGA binary and be done with it originally. What we now needed was a way to run only synthesis, no place and route, just synthesis and get the numbers. And then to check these numbers against the expected result. We also need a way to report our results in a nice looking fashion, like you saw earlier with VUnit. And a way to run builds in parallel. And we actually started out doing this ourselves. And then we realized that we will have to handle threads, and we will have to handle interrupts, and we don't want to deal with that kind of stuff. And we also realized that we already use a project that does this. So our Mr. Python, Lucas, set about seeing if we could take these parts from VUnit and use them in TS-FPGA. And turns out, of course, that we could. So let's transplant the brain. We'll take a dive into the VUnit test runner and how it all comes together. So what happens when you press run in VUnit? The first thing is that you get a test list. And yeah, you can hear what it is. It's a list of tests. And in the case of VUnit, that list is filled with simulation objects. For example, independent sim test case, I guess this is the most common. Yes. Yeah. Yeah, structured and simple enough. A reporter is created, which collects reports from running test cases to get the output to you as a user. The runner is created, which is the part that is going to actually execute the test grid. And then you hit run with the runner on the test list. So the runner is given the list of tests to make, and it starts. The first step is to create the scheduler, which is very much the saucy part that we wanted at the beginning. It handles threading, so if you gave VUnit 8 threads, it will make sure that all are always occupied with the test. If you hit Ctrl+C to abort the tests, it will clean up nicely. And with the scheduler, we can start the tests. As the tests complete, you need some object to handle the result of the test, so you can print at the bottom. And there's a test result object for that. So, this is how VUnit works in this regard. On the next slide, we will see how we overload some of these objects in TS-FPGA, just to, okay, we inherit from them and then we just adapt what we needed in our use case. So, how does the TS-FPGA build runner work? When you hit run, you create a test list. This time, the test is not a simulation, but the test is a build. So we need our own class, which is a build project. We already had that part largely, but needed to wrap it up in a way that mimics the VUnit test case and responds to the same kind of stimuli. Yeah, and then we need a reporter. And instead of using the VUnit test reporter, we use our own build reporter. The major difference being that we like to report things a bit differently. We have more results that we wanted to print. So, based on the test report class, it's these three functions that are overloaded. We then create a runner, and instead of a test runner, it's a build runner, which is based upon the VUnit test runner. Again, three methods to overload. And the primary difference being that VUnit will always purge the output path before beginning a simulation. But when you have a without a build project in there, you don't really want to wipe it every single time because, yeah, you know it may take some time to set it up. And then we hit run. Use the build runner on the test list. And then from here on, everything works as in VUnit. So we don't ever need to touch threading because the scheduler is already in here and inherited. Last little step is the test result. In our case, it's called the build result. Again, the reason for overloading this is that we want to print more information. We want to print how many lots and flip-flops the design used in the summary at the end. Yeah. We're actually approaching the end of this presentation already. So we will have time for another demo. So, with TS-FPGA, we have one entry point again for the builds, just as with simulation. So in this script, I wish I had this on my small screen as well. That just lists all builds that are available. Very similar to VUnit, right? So here we have just 4 builds, but these are our top level builds. In this case, we want to run our netlist builds. We just build submodules and check the sizes of these. And then we have 64 different builds for our users. These are test cases, right? We're not going to build 64 in parallel on this laptop. We will build a few of them, so let's run the Axie interconnect again. Let's see how many we have. We have 4. And we can run 4 in parallel. You can see the information here, what kind of project is. This is a Vidlid necklace project. It's just a normal Vidlid project if it's a normal FPGA build. It says top level and generics. For our FIFO, which is open source, and I'm going to show you a link later, we have a lot of generics, so the name is like this long. And obviously, if we make small changes to that one, and we really want it to be small, we need a way to control it, but all the configurations are always decent size. It's where this very much comes in handy. Okay. Yeah, now it fails. Because it complains that it already has files at output path. As I told earlier, we don't want to automatically wipe them. So if you try to launch a build and there's already a project there, it just fails instantly. And then I have to explicitly tell it to use any existing project. So now 4 builds have been started, and while we wait for that, we can look into the Python code for controlling this. So, in our case, the Axie interconnect is one library, a VHDL library, and with that library we have a module Python file. You can see it's called module Axie interconnect. It does a few things. Most importantly, this is where we set up VUnit, like you would do in your random Pi. And this is also where we set up our build projects. So this is one of the projects that's currently building. We specify what kind of project it is, the top level we're using, any constraints if this is a real FPGA build. And here we have the build result checker. That in this case specifies the total number of lots should equal 352. And then you can select here which kind of resources you're interested in, like if you make a multiply accumulate implementation, you want to make sure that it uses 1 DSP, not like 10 DSP, right? And if you want to be a bit more relaxed, you can tell it to use less than 400 lots instead of exactly equal to. A nice side effect of having this specification is that you can build it into documentation. So this is another open source project of ours, which is HCL modules. If you're interested in this, I strongly recommend that you look into it because it uses TSFPGA, and you can see how all of this is configured. Also, if you need a good small FIFOs, we like to brag about this as well. And part of the bragging is this table. So this is taken from the test specification I showed earlier, but for the FIFO module. So for all different kinds of generic setups, we have the expected numbers here that we can check automatically. So that's done both for the open source project and for our IP as well. And I think the fan on my computer is silent now. That's scary. I have backup now. Everything is run. You can see it's very similar to the VUnit because it's VUnit that's producing this output. And at the end we have a bit of a different result printout. As I mentioned earlier, we generally want to know the size in a format that's easy to read without having to dig into logs. So we print it here, and you can see that everything passed. If it failed, you will see it in a specific message. So let's get back. That's really all. These are the projects that were involved in the presentation. Vidlid, obviously. TS FPGA as the FPGA project manager. And then HDL module as a reference if you're interested in just checking out how this is used. Or need FIFOs and resynchronization blocks. It's a permissive license. And it's written by Lucas, so it's good quality. Say hi, Lucas, you weren't here earlier.
Hello, everyone. Could you go back so we see the links? That's what I want to see.
Sorry.
If we can get photos.
Questions?
Yeah.
If one would like to use this abuse that you have just shown us, which one of the links should we go to?
It's if you want to use it yourself,
Yes.
or if you want to use it through TS FPGA.
As you tell me.
I would say if you want to see how it's done, it's TS FPGA, because that's where it's done. And if you want to see it in practice, then you should go to HDL modules.
Thank you.
You have something?
Do you support different synthesis strategies for different netlist builds?
No. But I think you're going to add it.
I just might.
What was the question?
If we support different synthesis strategies for different netlist builds. I don't think so anyway. Lucas perhaps has a better answer.
I mean, it's very possible that you're a little bit hacky, but
It's not out of the box, right?
yeah,
So-
no,
Yeah.
not really.
Are we planning to support LiberaSoc?
Let's talk about that.
I will get back to you.
Yeah, wonderful. Yeah, any other questions?
Sorry, did you say that it was a bit hacky?
I mean, yeah, what you need to do is you need to add a tickle file that defines your synthesis strategy. And that you can do with the constructor of the Vidlid netlist project class. So you add that. And then you need to supply another argument to the Vidlid netlist project constructor where you define the run index. So if your tickle file creates synt4, and then you can specify 4 as the run index for the Vidlid netlist project. So I mean, it's not the worst thing in the world.
I thought it was amusing that you described it as being a bit hacky when almost this entire project is a bit hacky. Because you're abusing something.
The amount of hack is, yeah.
Still, it was better than the alternative.
We can show you on the laptop later how to do this custom run if you want to.
Yeah. Just point at what Lucas just said. Here now, for our own build, we have overloaded the Vidlid project class, so a true stream Vidlid class. It's very similar, but you can add your own stuff that you need on top. And the Vidlid project class has a tickle sources parameter, where you can add all the tickle stuff that you need.
Yeah, and also the run index, right? I don't have my glasses, so I barely see, but
Yeah,
default run index,
yeah.
you define like that.
Yeah, so you can have different strategies in that way and select one of them. So yeah, okay, correction, it's possible. It's not very much beautiful, but it's possible.
As you said, it's better than the alternative.
Yep. Very well.
I think we say thank you, Ludvig.
Thank you.